Hey, welcome. Let's talk about corrosion. So corrosion, like I have right here on the screen, is an electrochemical process in which a metal reacts with substances in the environment, returning the metal to an ore-like state. We're going to be focusing primarily at looking at iron and the way that iron corrodes. Iron's really interesting in that when it corrodes, it actually peels back layers, allowing for more iron to be exposed. So some metals, when they end up corroding, end up actually making this protective corroded layer that protects the rest of the metal from being exposed to oxygen and so on. But when iron corrodes, it flakes off, revealing more iron underneath that then can corrode, and this continues and continues, which results in structures being destroyed from the rusting that occurs. So iron, although it's an incredibly useful metal and is, widespread use and it's cheap and expensive, it has that quality of the corrosion of it, makes it very weak because it peels off in layers. So most metals like aluminum or iron corrode, while other metals like silver and gold are noble because they are weak reducing agents and don't normally corrode. Any metal appearing below the various oxygen half reactions on the redox table will be oxidized in the environment. So the word noble is an interesting one that we use quite a bit in chemistry. You of course know about the noble gases group 18, which means unreactive. So when we talk about noble metals or a metal being more noble, what we're saying is that that metal is less reactive. So when we're talking about redox, we're saying that the metal is a weaker reducing agent than a less noble metal, which would be a stronger reducing agent. So iron is not a very noble metal. If I take a look, these are the reactions that I'm mainly concerned with when I deal with corrosion, and it's oxygen reacting with stuff in a reduction half reaction. So this is oxygen and then hydrogen ions, so an acidic environment. Here's another oxygen and hydrogen ions to make hydrogen peroxide, H2O2. And then I have oxygen and just water to make 4OH minus. So all of these reactions are responsible for corrosion that takes place. You've learned in the past that when we have iron corrode, it makes always iron oxide, but that's not the case. It actually ends up being a mixture of both iron oxides and also iron hydroxide as well, but we'll get into that later. Now, when corrosion occurs, we actually have almost a little cell that forms on the surface of the iron that is corroding. So if I take a look, I actually end up with like this little battery that happens on the surface of the iron. So here what I have is a water droplet, and that water droplet ends up having ions in it because of the fact that I have iron 2 and hydroxide forming in this water as it corrodes. The more electrolyte I have present, the faster this will happen because it's providing more of an internal circuit. And then the iron, being the conductive material, ends up actually being itself the external circuit. So one area of the iron will be the anode. Not that anode. The iron will lose electrons, forming iron ion. Here it's iron 2. And then the electrons go to react with the oxygen in order to make, with water, hydroxide ions, OH minus ions. And those OH minus ions then end up migrating towards the anode, while the iron 2 or iron 3 that forms by the anode ends up migrating towards the cathode because it's a cation. And then what happens is it meets in the middle and it forms a precipitate, which is iron, 2 or 3 hydroxide. And that's essentially what we have for rust, is a mixture of iron oxides and iron hydroxides primarily, which is because of this iron 2 forming and this hydroxide forming and then meeting up and making that precipitate compound. So these are the two half reactions that are primarily responsible for rust forming. So oxygen, we all know that oxygen is very involved in rusting. I have oxygen in the water, so it will meet up and kind of dissolve in the water, but be in there. And then I end up adding the electrons, and that gives me 2 hydroxides. And then for the iron, it's just oxidizing to make iron 2 and 2 electrons. What's interesting is looking at the voltage for this. So I have positive 0.40 volts right here. And then when I'm actually looking at my iron reaction, which I don't know if it even shows up on this particular screen. Maybe it'll be on the next one, I hope. Oh, maybe not. All right, let's go back a few more. This is not pretty, but we're in the video and we're not going to restart it. So if I go back to a redox table, whoa, I've got to go way back here. I have one right here that I can use. So what I have is iron, which is right here. And then I have my oxygen and water to make 4-hydroxide. This is my SOA typically that I'm dealing with. So I have positive 0.40 volts minus negative 0.45 volts. So I get a voltage of positive 0.85 volts. So you actually have these little currents that are going through the iron metal as this corrosion is taking place, because the iron itself is acting as the external circuit. So next part of our discussion is what causes iron to corrode more quickly, and then how can we prevent it? Well, one thing is iron corrodes more quickly when I have more electrolyte. So as I have more ions, ionic compounds dissolved in water, then I end up actually getting faster corrosion because I have a better internal circuit. I have more ion movement that can go back and forth. So this is why salting roads, for example, really causes corrosion to speed up. Medicine Hat doesn't actually salt the roads. Instead, they use sand. And part of the reason is that causes less damage to iron structures because we don't have the ions then floating around, causing things to corrode more quickly. If you go to centers where they use salt, you'll actually see that the cars there rust much more quickly than they do here. Try going to the West Coast and taking a look at cars there and look underneath, and they're often just starting to rust right out at the bottom because of the fact that the ions speed up corrosion. Another thing is acid. As I have more H positive, I have more of these reactions where hydrogen ions are involved, which are stronger oxidizing agents, this one and this one, for example. So as I get to more and more acidic environments, lower pH, that speeds up corrosion. So this is where things like acid rain cause damage to structures because of the fact that I'm introducing a stronger oxidizing agent. So typically you want to have low ions and essentially close to neutral, right? Now acid is especially bad because not only is it giving you a stronger oxidizing agent, it itself is more ions, right? I have anion with that and the hydrogen ions, so it speeds it up even more. So how can we prevent corrosion? Well, there's a few methods. One way is what we call the barrier method. This is really simple. You paint it, you cover it with wax, something like that. And when you use the barrier method, you're stopping water and oxygen from getting to the surface of the metal. And by doing that, then it can't corrode because there's no surface where it's in contact between the SOA and the SRA, right? If you're taking away the water and the oxygen, the SOA, where it can't meet up with the iron, then I'm not going to have corrosion taking place. So this is why it's really important to make sure that if you have a scratch on your car or something, that you cover it up. That's also why wax is a really good thing, because it again adds to the barrier method. Galvanization is covering something in a zinc coating. Now, zinc is interesting when I coat it because it does two things. Number one, it provides this barrier where it separates the iron from the water and oxygen. And zinc, when it corrodes, when I get zinc oxide or hydroxide, it makes a protective layer so that we can't actually have more zinc being exposed all the time. So it just creates this layer of zinc oxide and zinc hydroxide that the water and oxygen can't get through, and it doesn't flake off. Now, another thing that zinc does is if I do have a scratch past the zinc is what we call a sacrificial anode. So if I go back to my redox table, zinc is a stronger reducing agent than iron is. So that means that zinc will actually corrode and go through oxidation before the iron does, which is great because in that case, I'm saving the iron at the expense of the zinc. So sacrificial anode is when I have something that is a less noble metal that is connected to what I'm trying to save. So it's a less noble metal. Often it would be something like aluminum, magnesium, zinc, and it oxidizes instead of the iron. So it's saving the iron by oxidizing instead, which is really neat. So that's how a sacrificial anode works. So for example, in the ocean, when they have iron structures, they'll put like magnesium or zinc blocks on there. And what will happen is the magnesium will get eaten away. And then once it gets close to the end, if it's almost used up, well, then they'll put another magnesium block on there. And that protects the iron from corroding because the magnesium is corroding instead. We actually have these in hot water tanks. There's a sacrificial anode that is inside of your hot water tank that protects the iron itself from corroding in the tank. You can replace the sacrificial anode and it can actually help your hot water tank to last a lot longer because it gets eaten up. And then once it gets eaten up, your tank starts rusting from the inside out, and then you start getting leaks. You can tell this is happening because the color of your water will actually start to go slightly brown from the tap when it's hot water, and that's because your sacrificial anode is gone, and now the iron of your tank is getting eaten away. Another thing we can do is we can use a trickle current. So that means that we're pumping electrons, into the iron. And if I'm pumping electrons in at a high enough voltage, what happens is the iron can't go ahead and form iron 2 positive and 2 electrons because I'm pumping electrons into it, forcing it to go the other way around. So I'm basically making this like an electrolytic cell where it can't oxidize because I'm causing the electrons to instead to be pumped in so it can't go out. This is something that could be used in something like an underground iron tank. Like a storage tank of some kind, where a trickle current will be pumping electrons into that iron tank, and then it can't corrode because the electrons are going in. Of course, that tank can't be having something flammable in it, because if it did, and then I have electricity going through it and there's a spark, that could obviously have pretty horrible consequences. So those are some methods for preventing corrosion. This is the sacrificial anode found in hot water tanks. So this is an old rod and a new rod. And typically these are made out of aluminum for hot water tanks. I replaced one at one point. It was really neat to see the old one completely just worn away. And then I put a new one in. Unfortunately, I was too late on that and I had too much damage done to my hot water tank already before I replaced it. So I couldn't make that work. I couldn't save the hot water tank. But if I would have done that, half a year earlier, I would have gotten way longer out of that hot water tank and I wouldn't have had to replacement. You can buy these suckers at Home Depot. They actually carry these sacrificial anodes that you can put yourself into the hot water tank and then you're good to go. Often the warranty itself on hot water tanks is based on how large the sacrificial anode is that they have inside of the tank, which is kind of interesting. All right, so that's it for corrosion. What's really important to know about this is that you understand this diagram right here, the half reactions that are responsible, which are the water and oxygen half reactions, right? And then we have the hydrogen ion in the mix as well, as you saw in this diagram. Wait for it. This diagram right here where we have oxygen and hydrogen ions. So these are the ones that are responsible as always for corrosion. And then I have, of course, iron that is oxidizing to make iron 2 and iron 3. These meet up to make flaky rust in the middle. And this is responsible for massive amounts of damage as iron corrodes away and then needs to be replaced. All right, that's it. Have a good rest of your day.